let's get some practice doing 3D sketches of organic molecules. I have shown here a number of condensed formulas, and so let's get some practice drawing Lewis structures, and then from there drawing 3D sketches. So the first thing we want to do is take this condensed formula and show its connectivity, show the skeleton of the molecule. So the CH3 we could draw as having 3 hydrogens attached to the carbon, and then a CH2. Remember, hydrogen only wants one bond, so as soon as we attach it to the molecule, it's done with its bonding. And there's a third carbon, it's another CH2, and a fourth carbon, and then finally there's a carbon, and then a nitrogen. Okay, so we show our basic connectivity, our skeleton, and now we want to try and fill all the octets that we can. And remember, carbon wants to have 4 bonds. If it's going to be neutral, stable, it wants to have 4 bonds. And nitrogen wants to have 3 bonds and a lone pair. And so if we arrange it to be a triple bond between the carbon and nitrogen and a lone pair on the nitrogen, then that would satisfy everybody's octet, and it would make every atom neutral. We could count for carbon 1, 2, 3, 4. Carbon has 4 and wants 4. Nitrogen 1, 2, 3, 4, 5. Nitrogen has 5 and it wants 5. So both of those would be neutral. So we have our complete Lewis structure. Now, in order to do the 3D sketch, we need to consider the hybridization for each atom. So for every single atom, hydrogen, of course, doesn't undergo hybridization because all it has is an s orbital. There's no orbitals, atomic orbitals to mix, so it always just brings in its s orbital. So let's think about the hybridization. This carbon has 1, 2, 3, 4 regions around it, and any carbon that has 4 regions to accommodate undergoes sp3 hybridization. And so that's going to be true for every one of these carbons that has 4 single bonds. It's going to be sp3 hybridized. Okay, now we get to this next carbon. It still has 4 bonds, but the 4 bonds are arranged differently. They're grouped differently. And now we have 2 regions of electron density. We have the single bond and we have the triple bond. So when you have 2 regions of electron density, we need sp hybridization. And the same with the nitrogen. We have the triple bond and the lone pair, so it's sp hybridized. And now the hybridization is going to dictate the geometry, so now we can start to build our molecule. We know that sp3 means tetrahedral. In order to draw a tetrahedral atom, we draw 2 of the bonds in the plane, like so. We can draw the hydrogen and the carbon in the plane. Remember, this bond angle is about 109.5. So the way we draw that is, we know what 90 looks like. We draw it a little wider than 90. And the other 2 bonds are going to be down in this area. One's going to be a wedge coming out towards you. One's going to be a dash pointing away from you. So it doesn't matter which is which, but we draw 1 wedge, we draw 1 dash, and those are going to be the other 2 hydrogens. So there's our first carbon, and it's tetrahedral. So now we come to the next carbon, and the next carbon, we've drawn 1 bond in the plane already. Now there's going to be a second bond in the plane, and where's it going to go? Now we want to resist the temptation of drawing it out like we did in our skeleton here, because straight out here it would be 180 degrees, and we don't have 180 degrees. It has to be bent 109.5. So that means we can either draw it in this area, or we could draw it on this area, your choice. Let's go down here. Okay, and if these are my 2 bonds that are in the plane, that means my wedge and my dash are up in this area. Again, doesn't matter which one is the wedge and which one is the dash. There are my 2 hydrogens. Okay, now we come to our third carbon. This bond is in the plane, so the second bond is either up this way or down this way. And we're going to kind of end up having a bit of a zigzag shape to our molecule. So I did this one up, so I'll go to this one down and this one back up. My dash and wedge are down here. One, two, three, 1, 2, 3. This is my last CH2. So here's my first bond. Here's where I can draw my second bond in the plane. So my wedge and dash are up in this direction again. So notice when I have a zigzag up, my dash and wedge and up. When I have a zigzag down, my dash and wedge are down. Okay, 1, 2, 3, 4. 1, 2, 3, 4. And now we're ready for our sp hybridized carbon. And what is the geometry for sp? When you have two groups, we put them linear, 180 degrees. So here's the first bond. So the second bond continues in that same direction. And the nitrogen is also sp hybridized. So what you could do is you can kind of draw a line continuing out and put the lone pair at the end of that line, or you can kind of draw the sp orbital in the plane in that direction and put the lone pair there. Either one of those would be good. But we also want to show these pi bonds. We have two pi bonds and we need to show that electron density here. So remember, the way we make a pi bond is we have two aligned p orbitals that are overlapping. So if this is my x-axis of the p orbital that was used to be hybridized, then the py is going to be perpendicular to that. So we could draw a py on the carbon, on the nitrogen, show them overlapping. Sometimes people like to put a lone pair here, kind of two electrons here rather, to represent the two electrons being shared as a pi bond. And then the second pi bond is going to be perpendicular. The p lobe is coming straight out and then straight back. So maybe we can show that with kind of a wedged lobe and a dashed lobe sticking back, and whatever we do on the carbon, we'll do the same thing on the nitrogen, and then show them overlapping to represent the second pi bond. So that's kind of what our triple bond looks like. And a way to confirm that you've drawn a proper 3D sketch is to build a model. So here's a model of this molecule, and now notice this has lots of different conformations, so there are actually a lot of different drawings that you may have for it. But if we line it up the way we kind of did a zigzag. We started up here. I'm sorry, we were like this. Okay, so we started down here, we went up to the CH2, down to the CH2, up to a CH2, and then down, and then straight down in that direction. Looks very similar to what we drew. And again, we'll note that when we have an alkane chain like this, sp3 hybridized carbons, a lot of times we draw it in this zigzag. It's a little easier because if you don't keep going up and down, you can have the molecule kind of crash into itself. So this is really the most stable conformation, is the zigzag. And when we have a zigzag up, our dash and wedge are pointing up. And when we have a zigzag down, our dash and wedge are pointing down. Okay, so let's take a look at another molecule.